What's up, guys? Okay, so in this video, let's keep talking about the second part of the primitive roots of unity. And so this video, the goal is to prove the existence of primitive roots, mod p or r prime. Okay, so basically we are gonna to show that primitive roots always exist for the r prime. And the tool is basically this simple lemma. So this lemma says that if you have am equals to 1, and let's say your f is this exponential, the order. So basically, it just tell you that the minimum order for a is f. So af equals to 1 mod n. Then we have the order for ak is just the order for a divided by kf. Okay, so remember this is just the GCD. And okay, so in particular, if this guy is the same as this, right? That means that if only if that kf is 1. So basically that k is co-prime to f. Okay, so the proof is fairly trivial, right? So you know that you just, let's say x is the smallest integer such that ask is 1 mod n. Okay, then this will be the same. This will be the smallest x greater than n such that right by previous, you know that kx must be 1 mod f. Sorry, 0 mod f. It must be 0 mod f. Okay, but this is the same as this equation is the same as x equals 0 mod f divided by d, where d is just kf. Right, because if kf is coprime, then there's no the x must be the same as f, right? If kf is coprime, otherwise that you can just using GCD, right? So this is definition for the greatest common divisor. Okay, and in this case that if d is kf, right, then you can choose x, right? So you can easily just choose x to be this, right? So just f divided by kf, right? And so in this case that the kx will be the multiple of f. Okay. Okay. So yeah, just f divided by d. Okay. Right. So because d divides f, and d divides f, and also d divides k. Okay. So if kx it must be 0 mod f. Right, because right k divides, right, if you just kx, right, you can write it as k divided by d times f, and d divides k, right? So this guy's the integer and times f, right? So it's multiple of f. Okay, now we have a very weird result, so we can prove the existence. Okay, so theorem. Okay, so let's say p is r prime, and then d is the positive divisor of p minus 1. Then what? Then basically what we are saying to say this is every reduced residue system mod p, there are exactly 5D numbers such that a to the d is 1 mod p. Okay, so this also tell you that if you can choose d to be 5p, will be p minus 1, right? So if I choose d, okay, so right? So D is positive by divisor, right? So I can just choose D to be phi of P, which is exactly P minus 1. This show that there exists 5 P minus 1 primitive roots. Okay, maybe it's very hard to understand what the hell is going on here. So let's maybe do a very simple example. Right, so for example, I can choose P to be 7. And right, let's see. So our 5, 6 will be 1 and 5, right? So just 2. Okay. So that means there's 2 primitive roots for 7. Okay. So let's check it. So let's do this. Let's check it. Okay, so if let's say this is A, right? Choose A to be 1, 2, 3, 4, 5, 6. And we want to check its order of 7. Okay, so maybe it looks difficult. So we're okay. So notice that the 5, 7 is 6, right? So we need to find a guy which A to the 6 is 1 mod 7. Okay, so we want to find a guy which A to the 6 is 1 mod 7. And the theorem tells me that there are 2 of them, right? So there are 2 of them. Okay, so definitely 1 is not a correct one, right? So 1 is not correct. Right? And how about 2, right? So 2, if you or 4, 8, right? So 2 is not correct, right? Because 2 to the 3 is already like get 1, right? So 2 is also not okay. Not a go, not it's not a primitive root. So 3 is 9. So 9 is right, 9 is 2. Right? So you can just make it to be 2, right? Because I'm mod 7. Okay, and then 2 is like 2 for there you go 1, right? So it's like this tell you that right, so it means that 3 is 3 mod 7, and then 9 is 3, sorry, 2 is 9 square mod 7. Okay, and so you can see that 6 is 3 cube mod 7. And 18, right? So it's 4 is like 4, 3 to 4 mod 7. Okay, then you can see that this is the answer, right? Because so if you keep going, then you get 5 is 3, 5 mod 7. So finally you get 1 is 3 mod 6, 7. Okay, so this means that 3 is the primitive roots. 3 is a primitive root. Okay, and then you can check 4. I guess 4 maybe 4 is 16, right? 4 is 6, right? So 4 is not primitive roots. And then 6, 6, 36, so it's not primitive roots. So 3 and 5 are primitive roots, right? So there are exactly 2 primitive roots, as this theorem guaranteed. Okay, so this is just this theorem. And so this theorem is very interesting, right? It says that if you take t to be positive divisor p minus 1, then you will get exactly 5D numbers. So exactly 5D number means that this reduced system, every guy in this reduced system has exactly 5D numbers. Okay, of A to the D equals to 1 mod P. Okay. So this theorem is you stick a while that you can see how to prove this. Okay, so the tool is very weird, right? The tool is that at the number theory, we know that the 5D, D is a sub divide n is just n. Okay, so we can define of D to be an x. The x is from 1 to p minus 1. And the A to the D is 1 mod P. Okay. And then let's say the cardinality of A of D is called f of D. Okay. Right. So obviously f of D greater than 0. And by definition, right? So your f of D, D divides n should also sum to n, right? Because by definition, right? If let's say, so in this case that yeah, it's just sum of n. Okay. So this means what? I combine this and this, but what we got is following, right? So we get 5D, right? D divides P minus 1, right? Because I mean you choose n to be P minus 1, right? You say choose n to be P minus 1. And so f of d is disjoint, right? F of d is disjoint because either is okay. So I should notice I should not write this. I should write the d to be the minimum order, right? So the order of this, right? So different. This is the disjoint union of original set, right? The total has p minus one, right? P minus one. So in the beginning, you know this, right? By definition, and you also so this tell you that f of d dp minus one is also p minus one. Okay, and you stick to equation, right? And you get follow, right? You get follow. Okay, so this is trivial. Okay, trivial. Okay, so our goal, so basically it's just one thing, right? Our goal is to show 5D equals to f of d for every f of d is non-zero, right? This is enough, right? If you prove that for every f of d is non-zero, basically means that this small reduced system of d, each one has exactly the number of 5D, which finish our proof. Okay, so yeah, so the proof idea is that the proof is okay. So the proof is just the first step is that let's assume f of d is non-zero. So this tells you that f of d is non-empty. So f of d is non-empty. Basically, there exists a such that a to the d is one mod n. Okay, and also one a squared up to a to the d minus one. They are incongruent, right? They are incongruent. Mod m. By the way, so m should be p here. Okay, so 1a squared up to a d minus 1 are solutions of what? Of xd equals to 1 mod p. Right, it's trivial. You can prove this, right? Okay. But this equation, right? This equation has only these solutions, right? Because this is mod p field, right? So it's only these solutions. Okay. So all this must be the all solutions. Okay, so there's no other solutions outside this A. All the xd equals to 1 mod p must generated by all these solutions. Okay. Well, so we just need to ask. Right, so every there's no other solution, no other number in the from 1 to p minus 1 such that it satisfies xd equals to 1 mod p. Right? So all these solutions must be generated by that single A. Okay, so we just need to ask what's the case that if the order of this A to AK equals D. Okay, then by our results, right, previous lemma tell me that this unless that KD equals to, if only if KD equals to 1. Okay, then by definition, the number which makes the KD equals to 1 is just phi of D. Okay. So what? So there are 5D number f exponent d modulo p. Okay, so the idea is that all this d is the minimum for a, right? But maybe not necessary for a one or a square or other exponent, right? So in order for particular exponent, for still d exponent, there are only 5d of this. Okay. Okay, so let's finish the proof. So f of t equals 5t. Okay, the reason is as I said, right, because the only possibilities for f of d must come from this, must come from all this, must come from this, right? And in this there are exactly 5 of these such that satisfy this equation. Such that the exponent is still the order is still d. So this finish the proof. The proof is this is interesting. Okay, so hope you guys subscribe to my channel. So now we have like proof there's no primitive roots for 2 to the n, but there's a existence of primitive roots for r prime. See you guys next videos.